All right. Well, I'm just gonna get started here, and I'm trying to use this to kind of get you guys get your focus. Because apparently, if I cannot get your focus, Mr. Ballroom is very good at getting attention. So in case you guys haven't noticed, he's no longer the CEO of Microsoft. And from what I have heard or read, from multiple sources, a lot of people who were involved in Windows 8 were also fired. And here I am, hoping that Linux, open source movement will claim the glorious, win against Microsoft. And here it comes, it is a self-implosion. It's like, no, it has nothing to do with Linux whatsoever. Linux may exist or may not exist, and this will still happen, which is really kind of interesting. Microsoft is also going to buy or have an alliance with Nokia. And for those of you who have heard of it, they're trying to make Nokia X, which is a new line of phones, to combine the best of Android and Microsoft. So the underlying operating system is the open source version of Android, which does not include all the Google apps. And then on top of that, Microsoft will have its own developers to develop Microsoft applications to run on Android, and then they will package everything onto this Nokia X phone. If you ask me, it's a very, let's just say, risky idea. So that's I think that's where the company is heading. I mean, they really have no idea where to go, which is really kind of it shows you the limitations of a proprietary product. Open source product is kind of going in the opposite direction. Some of you know that Android is going to the desktop. So Android is going to the desktop, Chrome OS is on the desktop, Steam OS is on the desktop, set-top box basically. And then we have Ubuntu going in the opposite direction, going from desktop onto mobile devices, onto phones and stuff like that. Not every single one is going to be successful. There will be some products that will just be a flop, right? It's just not going to work out. But it's an ecology. So you're basically looking at one specimen in a zoo versus a swamp area that is bursting with a variety of lives. I think that pretty much describes what open source can do, as opposed to something that is from a single company and it is proprietary. The Europeans were not very happy with Windows either. After the NSA incident. Because they do not trust. They just don't trust Microsoft. Okay, they think there's no way they can prove the non-existence of backdoor when they install Windows 8. So that's just kind of. I just want to kind of bring it up because it's somewhat interesting. Things that I did not anticipate when I first started to switch to Linux about 14 years ago. I definitely did not see this day coming. I would see, Linux, and Microsoft, really duking it out. Microsoft would use legal ways to try to fight Linux, and then Linux will try to fight back, or open source will fight back, because it has, this massive amount of labor, as known as graduate students, to work on all kinds of different projects. Didn't quite turn out that way. As it turned out, IBM is one of the biggest contributor to the Linux project. IBM and Red Hat, both are for-profit companies, and they contributed a lot to the Linux and also open source projects. So it's really kind of interesting how it took on directions that people cannot anticipate. We are going to have a practice exam soon because we need to have the first midterm soon. So I'm going to give you an idea of probably by next Tuesday, I'll give you a practice exam, which means the actual exam is going to be 1 week after that. Okay? But the scope is going to be including everything, at least up to addressing modes. So the homework assignment that's due this Thursday will be a part of the scope of the midterm. Are there any questions about the homework assignment? No questions? Okay. Are there any questions about that line that says L2 colon dot int L2? Okay.
Can you talk about that?
Sorry?
Can you talk about that?
What is the question?
Can you explain that line?
I can definitely explain that line. L2 colon is defining a label, okay, where the label is defined to be the location of that particular memory location. At that location, dot int tells the assembler I want to allocate 4 bytes and initialize those 4 bytes to the value of the following expression. The following expression refers to L2. So did I answer the question? No? Yes?
So the address is the content of that line?
How about this? I give you an alternative, I don't know whether the typecast is really necessary or not, but I'm going to put it here. Now, since all of you have taken CISP360, this should explain it, kind of. Is that okay? Does everybody know what this C code is going to do?
But
Not exactly.
Put the address of the pointer in the pointer.
Yep, puts the pointer, this location becomes a pointer to itself. So if this thing is at location of 6,000, then it will be 6,000 as its own content, because its content is its own address. Yep.
Where does the value of L2 come from?
The value of L2 is a memory location where this dot int is allocated.
So there,
Every label is just a number. So when you say, L1 dot colon, let's say dot byte 0, that means this L1 is a number. You can look at it just as an integer, but you can also use it as an address. But the value or the integer this label is equivalent to turns out to be the address of this 1 single byte.
so is there any way to know what L2 is going to be before you actually run the program?
Nope, you should not depend on that. Okay, so you cannot know, what L2 is going to be, but you know that L2 is the location of the first byte of this dot int. That much you know for sure. Okay. Yep.
Is there any way to check the cache and see what's in the cache? I was trying
Check
to figure
the cache.
like L1 and L2, the library. Like I tried to just before moved around anything, just see what was stored in L1, L2.
You can use the X command to do that.
What is I couldn't find out the syntax to print it out in GDB.
In GDB?
Yeah. I tried
we have
X, percent or $L1, it wouldn't give it to me. So
Okay, so instead of giving away the answer to the homework assignment, I'm going to do this. We'll just make that. I'll just call it memory.
oh yeah. That's in figure it out.
Oh, I used the wrong command to do it.
I know I could put it into a location such as AH or AL and then check that. I was just wondering if there's any way to, not have to go through that process and just check it before I move it into memory.
Say that again.
Technically, I could move the L1 into memory and then check what's there.
Correct, but you don't have
but
to.
I was just wondering if I could check L1 before I transferred it to memory.
Okay, L1, L2, things like these, they are, everything is just a label, okay? And each label is defined as an integer. Now, in this case, the way I define this makes this the address, makes L2 the address of the first byte of the .int directive, okay? But I can also define, I'm going to write a sample program here just to show, what exactly is a label. So I can define L1 like this. I can say, L1, I think it is just an equal symbol to 25, okay? That just, basically says, okay, L1 is a symbolic name, and from now on, when I refer to L1, it's the same as referring to the integer value of 25. Okay, that's one way to define a label. If you read the notes, there's another note that says there's a dot symbol, which means the current location in the current section. Remember, we have a dot data section and a dot text section, right? Now, when you write code at any particular point, the assembler knows the current location. Okay, I'm allocating up to this point. I'm allocating up to this point. That point, which is the current location, or if you prefer the cursor, is the dot symbol. Okay, so you can also define L something. Okay, let's say L2 here. You can define it as the current location of that particular section. Is that okay? Okay, it's almost like you have a binder. Okay, let's just focus on dot data. Okay, so we don't have to worry about dot text. So I'm going to use dot data here. When you look at dot data, it is almost the same thing as you have a binder. And every time you say dot byte, it will allocate whatever number of bytes you want to initialize. Okay, so the next location that can be allocated is quote unquote the cursor or the dot. Am I making any sense? Because it has to keep track of how many pages have been allocated already, so that when you say .int, it will say, oh, okay, the next 4 locations start from here, and then the 3 more bytes after that. Okay. So it has a cursor to keep track of where's the last location allocated. All right, and the dot symbol is that cursor. As you allocate bytes, the dot moves along. So every time you refer to the dot, you're referring to the current location of that particular section or the next location that will be allocated. Is that okay? All right. So if I just do it like this, okay, I'm going to remove this one here. I'm going to say L1 equals dot. I put a dot in here. Doesn't matter what it is. I can just put in 0x, 1, 2, 3, 4, 5, 6, 7, 8, like so. And I have a dot L2 here. I switch back to the dot text section, which is just another section. Each section has its own cursor, okay? Because when you write code, like assembly code, each assembly code would also take up space. This program doesn't even need to assemble. I'm going to make it assemble and run anyway. Okay, so here's the start symbol, and it doesn't do anything useful. It just basically executes the exit code right away, because that's not even the point of this particular test program. The point of this particular test program is what is L1 and what is L2, and how do they relate. Is that okay? So if you want to visualize this whole thing, you basically say, okay, dot data is one section, and by the way, with this assembler, you can allocate as many sections as you want. But in this case, we're just using one particular section. So dot data starts at a certain location. So initially, before I do any type of allocation, it starts here. The dot is referring to the location, that the next location to be allocated, which is kind of like location 0, but we never know exactly where it's going to be. It's just the beginning part of this entire section. Is that okay? When you look at line 2, which is L1 equals dot, L1 becomes an anchor to this particular byte location. That's all it's saying. It is a bookmark. L1 is a bookmark of this particular location. The next line, which is dot in, 0x, 1, 2, 3, 4, 5, 6, 7, 8, is telling the assembler, I want to allocate 4 bytes because it's a dot in. And I want to use those 4 bytes to represent the hexadecimal number 1, 2, 3, 4, 5, 6, 7, 8. Okay? And because of little endian, we represent those bytes as 78, which is the least significant byte. And then we have 56. And then we have 3, 4. And then we have the last one, which is 0x12. So these 4 bytes are now allocated and initialized within this section. At this point, right after the dot int, where is the dot? Where's the cursor? Where's my next location to allocate?
Next one.
Right here, right? So at this point, right after the dot int, my dot is actually here. Now, at that point, which is line 4 of this code, when I say L2 equals dot, that means, oh, you know what? I want to put another bookmark here. It is called L2. So L1 is a bookmark, L2 is a bookmark. You can look at each one as basically a page number in this big, huge binder. You cannot depend on the actual absolute location of L1 or L2, but you can rely on the relative location between L1 and L2. So in this case, if I print L1 or L2 minus L1 as an expression, it should be 4, okay? Because we are using byte locations, and there are 4 bytes in between. Are we doing okay so far? Now, the mysterious code that you encounter in the homework assignment, which is L2 colon dot int L2, is nothing more than the same thing as this one here. Okay, let me just write it in the in this code. It is really the same thing as this. Okay, line 4 defines L2 to be this location. And line 5 is saying, I want to allocate 4 bytes, initialize those 4 bytes so that collectively those 4 bytes is L2 itself. That's all it is. Because L2 colon is effectively the same thing as L2 equals dot, which means it is the current location in that section. Is that okay so far? I mean, does that help explain what is L2 colon dot int L2? Okay. Now, the other thing you can do with programs like this is really just to go into GDB and examine the locations and find out exactly where how the memory locations are initialized, and you will probably find that it's kind of interesting. Okay. Is that helping or not? You have to kind of make the connection. I'm giving you all the little pieces, but I'm not supplying the actual line to connect all the pieces.
If you intended how you had it initially with L1 being outside of the dot data, are you just not allowed to do that? Or what happens if you define or create L1 as a label outside of a section?
Each section has its own dot, has its own cursor. So before I say dot data, it is in quote unquote the default section, which I think is the dot text section.
Oh, okay.
So by default, it is using the dot text section, but when you say dot data, then it switches to the data section.
So
how do the dot data and the dot text sections interact? Does it not matter?
How do they what?
Interact, like it's all one contiguous.
That's a good question. What happens is the linker will look at all the sections that you define in your program, and certain sections have special meanings, like dot text has a special meaning. So dot text as a section will be marked read only when you run the program, so you cannot have self-modifying code. Dot data and all the other sections have no particular meaning, so they are all basically just concatenated and become a part of the image to be loaded into memory before your program gets control to execute.
Okay, and also in the first homework, .global start was at the very beginning.
It doesn't matter.
Okay.
Yeah, .global _ start can be at the very end of the program, can be at the very beginning of the file. It doesn't matter where it is. In assembly language programming, there's no requirement to define a label or even to declare a label before it is used. So you can put it at the beginning, you can put it at the end, doesn't matter at all.
And that would be just the part, from the start to the exit code is the parts that are actually run.
From underscore start to
the exit.
yeah, those four. Yeah, this is a program that only contains one instruction, which is exit 0. That's all it's going to do.
Yeah, what I'm saying is it'll only execute the stuff that's between the dot start and the exit instructions, right? It won't execute anything else.
That is correct. Underscore start has a special meaning. It has almost the same meaning as main in C and C++. When the linker links this particular program, it looks for the underscore start symbol because in the executable it will use that underscore start symbol to indicate where do I start the execution of this entire program. Because I can put instructions before underscore start, the definition of underscore start, I can put instructions after that. So how would the linker know what is the first location to start the entire program? Well, the definition of underscore start is the entry point of the entire program.
So if you put a move instruction before underscore start, would it get executed?
Nope,
No.
would
Okay.
not. That's a good question. Any other questions? No other questions? Now, reading the links, in the on the website is going to be helpful. In other words, if you go to the website in topic 2 particularly, there's this link here. Also, there's useful GDB commands, so you might want to click on that one. That one is really short. That will be useful because the addressing modes is going to tell you, this particular one will also explain some of the stuff that you are asking in this particular class. It will explain what a label is, and also, oops, I just closed something that I did not intend to.
But you can right click and undo close, I think.
Hmm?
You can right click and undo close in the tab, I think. Like
Again.
you can undo close in tools somewhere. Then right click on a tab, and you can reopen and close tab and close the tab.
Oh, okay. Nice. Yep, so in here, basically, you have to read through this whole thing here and then, make the association between these concepts with the homework assignment itself. All right. Are there any questions about that, those instructions? How many people have assembled the program, get into GDB, and use the X command to take a look at what the bytes are and how they're laid out? Okay, was it useful to take a look at that?
It's kind of cheating, yeah.
It's kind of cheating. Well, it's not exactly cheating, but it does help you learn about how memory is laid out, and the purpose of the homework assignment is 1, to make sure that you understand how memory is laid out, and 2 is to have a good understanding of the addressing modes. Are there any other questions related to the homework assignment? Because I think that L2 colon, dot int L2 is the really only mysterious one. Yep.
For assigning a negative number, do we need to assign it like hexadecimal, or we can use decimal?
To specify the underscore locations, you can use anything. I mean, the underscore is just a placeholder. So you can use a label, you can use a particular integer if you want to. You can use an expression if you want to. Like an entire expression is fine. If you want, L1 plus L2, the whole thing divided by 2 times, something, hey, you can use that too. So any expression goes. You just cannot change the addressing mode itself. That's the only thing you cannot do. Okay. Any other questions? No other questions? All right. If there are no questions, if you can think of any questions, go ahead and ask me. But if you otherwise, we'll go ahead and continue with the flags that we were talking about last time. So I'm gonna bring up these other ones. Okay, so arithmetic operations. We kind of talked about this already. We talked about signed versus unsigned interpretation. We talked about the two's complement mechanism. Are there any questions regarding the two's complement mechanism? 2's complement, which is a bitwise operation, is equivalent to negation in arithmetic. That's basically what it does. Are there any questions about 2's complement? No questions about 2's complement? How do I know a number is negative if I know ahead of time that I should look at those bit patterns as a signed number? How do I know? Go ahead. The most significant bit is a 1 if it is representing a negative value. So if the most significant bit is a 0, it means it is a non-negative number. All right. So that part is good, taken care of. We talked about the 4 flags. Okay, the first flag is the 0 flag. The 0 flag has a value of 1 if and only if the result of either an add or a subtraction is 0. Okay, so if you look at a 4-bit number, I'm going to use a mouse pad as my whiteboard here. So if you look at the result of an addition, so let me go ahead and just give you a hypothetical addition, which starts with a number starting with a bit A, and these 3 bits I don't even care what they are. Okay, the most significant bit of the second number is B, and I don't really care what the other bits are. Okay. This is the final carry. This is the actual result. Well, with the actual result, I have to label each one, so it becomes W, X, Y, Z. Now we want to define those 4 flags that we were looking at, that we were talking about last time. The carry flag is itself, okay? So C is the extra carry flag, carry or borrow, depending on the operation flag. The Z flag is indicating whether the result is 0 or not. In this case, W, X, Y, Z is a 4-bit number. How do you represent 0 as a 4-bit number? 0, 0, 0, 0. So that means W, X, Y, and Z, all of those bits need to be zeros in order to represent the actual value of 0. Is that okay? Mm-hmm. Okay. So that means the Z flag can be defined as such. It can be defined as the negation of W or X or Y or Z. Because if you look at the OR operation inside the parentheses, if at least one of those bits is a non-zero, the entire thing is going to be a non-zero. But when you take the negation of non-zero, or if you take the negation of true, it becomes false. Is that okay? But what if the number itself is actually 0? In other words, what if W, X, Y, Z are all zeros? Then the disjunction becomes, what will it become? It becomes 0 or false, right? And what is the negation? What is the logical negation of 0 or false? True. Exactly. So the Z flag becomes 1 to indicate the result is actually 0. Let's take a look at the next one. The next one is really easy, the sign flag. The sign flag is the most significant bit of a number or the result of a number. And which one should that be now?
W.
W. That's it. Okay. The most complicated one is actually the overflow flag. The overflow flag is a 1 when the sign of the result does not make any sense. Okay. So in this case, I'm dealing with an addition. So that means if I add a non-negative number to a non-negative number and somehow end up with a negative number, the sign of the result does not make any sense. Right? Because if you add 2 non-negative numbers, you should always end up with a non-negative number. You can also say the sign does not make any sense when I add 2 negative numbers and somehow end up with a non-negative number. So in order to represent that, it becomes something like this. Okay, there are 2 scenarios to take care of. In the first scenario, A is asserted, or A is a 1, B is a 1, but W is not a 1. This particular case takes care of what if I add 2 negative values and end up with a non-negative value. Are there any questions about this part here? Why it is representing one case when the sign of the result does not make sense for addition? questions?
For positive numbers?
Okay, so for non-negative numbers, we have the second case of the disjunction. In this case, we have not A, which means A is a 0, not B, which means B is a 0, but somehow the most significant bit of the result W is a 1. And this expression, which is not really simple, but combined, if you combine the two sides using the disjunction in between, it becomes the actual logical equation to define the overflow flag. Any questions about the definition of C, Z, S, and O? These are all the flags that you can use for conditional branches, and that's how you can make branches in assembly language programming. That's the only mechanism that you can make conditional branches.
What is the Z flag again?
The Z flag is called a 0 flag, which means is the result of the operation just a 0. It only looks at the W, X, Y, Z. It does not take C or the carry flag into consideration. Should we do an example? We did some last time. Yep, go ahead.
So the right side is taking positive, and the left side is negative.
You mean for the overflow flag?
Yeah.
Okay, for the overflow flag, this side is saying, I'm adding two negative values and end up with a non-negative value. The other side is the opposite. I'm adding two non-negative values, but the result is negative. Okay. Any questions about this? Now, can we extend this to 32-bit? This is a 4-bit, definition. A 32-bit, definition is going to be about the same, except, we have a whole lot more letters to represent the result. And those are only required for the 0 flag. Is not required for all of the other flags. Yep.
How about the initial state?
The initial state of flags?
Yeah.
It doesn't really matter, because you would not be testing for those flags unless you have done a compare, add, or subtract. But I have no idea. They should be initialized to some default value when you power up the processor, but it really does not matter to us. Okay. Any other questions about these flags? What about subtraction? How about subtraction? So if I have A unknown bits minus B unknown bits, can come up with the result. The result has a standalone borrow flag, and it also has W, X, Y, Z as the result of the actual subtraction. C is the borrow flag in this case. Z is the same as before. I'm just going to be lazy and copy and paste these two, because these two are really the same as before. Oops. There we go. But the last one is now different, because when you're dealing with subtraction, when is the sign not making any sense? Can someone tell me, when the sign of the result of a subtraction does not make sense?
You subtract a negative number from a positive number and get a negative number.
Okay, that's one case. You subtract a positive value from, you subtract a negative value from a non-negative value, and somehow end up with a negative value. Okay, that's one case. So how do we express that? Okay, the first number is non-negative, which means A is a 0. Okay, if A is a 0, we take the negation of that, so that this becomes positive, becomes a 1. And B is a 1 because you are subtracting a negative value from a non-negative value. What about the result? The result being W being 1 makes it not make sense, right? Sorry?
W.
Yeah, but do we want W or the negation of W in this expression?
W, because
We just want W because when the result is negative, then it doesn't make any sense. Okay. So is everybody seeing why this particular conjunction indicates that the sign of a subtraction does not make any sense? Is that okay? All right. So the other one is really kind of just the flip side of this, because the other one says if you subtract a non-negative value from a negative value, and then somehow the result is non-negative, then it also does not make sense. The sign does not make sense. Is that okay? And that's the actual definition of the overflow flag. It takes a look at the most significant bits of the incoming number that you're supposed to subtract or add. It also takes a look at the sign of the result of the operation. And then it feeds those information into this equation. And if the result of this entire equation is a 1, then the overflow condition happened. Which basically means you want to represent, or the result of the operation is out of the range of the representation ability of the number of bits that you're supplying. That's basically what it means. Okay. Are there any questions about all of these things? Yep, go ahead.
Can you list all instructions who affect like all?
In this class, we'll just use add, subtract, and compare.
And
Move does not change
multiplication.
it. Multiplication, at some point we'll get to it too, but right now we don't. We are not too worried about multiplication. Okay. Multiplication is interesting because the instructions add, subtract, and compare are sign insensitive, but multiplication is sign sensitive. So that's why we don't want to deal with multiplication for the time being. Okay. All right. So are there any questions about this? Let's go through some examples, just to see how the flags are reflected in GDB, and then we'll talk about conditional branches. In other words, how do we make use of these flags? Okay. There are only really 3 instructions that we need to know. If I go back to the notes here, let's see, the flag. Okay, that's the one. So if I go back up. There are only 3 instructions that you need to know, and it's all here. We have the add instruction, we have the subtraction instruction, and also the compare instruction. Those are the only 3 instructions that we need to know at this point that will change the flags. The add instruction is pretty simple. It has 2 operands. The sum is stored in the second operand. In other words, it is just like the move instruction. Because in the move instruction, the second operand is the destination. In this case, it is also the case. It only takes 2 operands, it adds up the numbers, but the number is stored, or the sum is stored to the second operand. ADC, we'll talk about it later. We'll move on to the next instruction first. So here's an example. Well, this is an example involving add with carry. So we'll deal with that a little bit later. The next instruction is subtraction. Subtraction works pretty much the same way. You just have to know which number is subtracted from which other number. The first operand is subtracted from the second operand, and then the result is stored in which operand? The second one. Okay. So in the AT&T notation, the second operand is always the destination, the one that is storing the result. But you have to remember, we are subtracting the first operand from the second operand in this case. And the last instruction is the compare instruction. And you can see compare instruction only has 2 sentences. Okay, the first one is, okay, CMP is the abbreviation of compare. And then the second sentence says it's basically the same as subtraction, except we don't store the actual result. So it goes through all the motion of doing the subtraction, but it does not store the result. The result is there, okay? It actually computes the result, but it is not stored to the second operand. And it is useful because sometimes we just want to do a compare. We do not intend to actually change something as a result of the operation. Question? Okay. All right. So with all these discussed, let's go through some sample programs and see how the flags are affected by some of these instructions. Yep.
How does compare tell you which number is greater?
That's a very good question. Let me just repeat the question for the sake of the recording. How does compare know which number is greater? Is that what the question was?
If it doesn't store the difference, then how does it
How do you use the result?
Yeah, how do you see the result of it? compare?
The flags.
Oh.
The flags are the ones that are indicating the ordering of the numbers that you're comparing.
Zero flag. Zero.
The zero flag is useful to see whether the two numbers are identical or not. But when you're looking for which number is actually larger than which other number, then you have to pay attention to the other flags. The C flag or the carry flag is useful for certain types of numbers, and then the overflow and the sign flag, they have to be combined in order to be useful. Each one is not useful by itself. Okay, so we'll take a look first, at how we use these instructions and how do we use GDB to help us, visualize and get some hands-on experience with these instructions. So I'm going to take out this particular program, because it's not that useful. I'm going to start with, we'll just have one folder to deal with add. All right. So we switch to the .text section, which I think is actually the default section to begin with, but it doesn't hurt to say, okay, I really want to switch to the .text section right now. .global_start, which means export this label _start. The linker needs to know about it, and then we just say _start, and we'll go ahead and just do something with byte. Okay, so we'll move byte 0x. Well, let's just do zeros for now. Okay, so we'll move 0 into %AL. This is my first register, and then in the second instruction, I'm going to use add byte. So add and subtract and also compare, just like move, can be used without a with indicator, without a B, a W, or an L, but it is usually a good idea to make it explicit. In other words, you use a B to indicate a byte-wide operation, a W to indicate a word-wide operation, and an L to indicate it's a long word operation, 32-bit. So in this case, I'm limiting myself to 8-bit operations. I'm adding another 0 to AL, and that's it. That's my entire program. Just to make the program complete, I'm going to finish it up with these instructions, which I probably will not even run in anyway. But I'm just putting it here just so that this program is complete. Okay. And now we go into GDB. This program, if you run it by itself, it's not going to be very helpful because all it's going to do is this. Not exactly helpful. Okay. So what we want to do is to use GDB to run the program and put a breakpoint on line 7. Well, we're going to put a breakpoint on line 4 just, so that we can single step each instruction. Okay. Run the program using R, and now we are about to execute the first instruction. Let's take a look at E flags, which is the register that contains all the flags. And this tells you that the carry flag is cleared, the sign flag is cleared, the overflow flag is cleared, and the 0 flag is also cleared. Because when you look at the square bracket next to it, you only see IF, okay? But IF is basically the interrupt flag. The interrupt flag is set at this point. But you don't see OF, which is the overflow flag, ZF, which is the 0 flag, CF for the carry flag, and what is the other one? The sign flag? Did I mention the sign flag already? But you don't see any one of those, so that means they are all clear. Okay? Yep.
Does the IF flag show up because you put a break, or is that just
No,
always going to show?
it
What's
is-
the IF flag indicate?
Because the interrupt flag is always enabled in a normal program. So the interrupt can happen in the background, so when you have a hard drive, the hard drive is done copying some bytes, it will interrupt the processor and say, do I have anything else to transfer? Or if your NIC, if your network interface card, receive bytes, it would also cause an interrupt to tell the operating system, I just got a frame, what am I going to do? What are you going to do with it? So that's why the IF is set, usually. Okay. All right. So let's go ahead and single step this instruction. Okay, now I should have 0, 0 in AL. Let's double check. IRAL, the low byte of EAX, it certainly is 0. Okay, no big surprises there. But let's take a look at the flags again. IRE flags. and it is still without the 0 flag set. So this tells you something. It tells you that the move instruction does not change any one of those flags. Okay? Which is actually a very useful thing. Okay, you don't want the move instruction to accidentally, change the flags. All right, so we are now about to execute the second instruction. This is the instruction that we are about to execute right now. It is an add instruction. It is supposed to change potentially some of the flags. So we single step, and well, first of all, we check the result. What do you get when you add 0 to 0?
0.
Okay, no big surprises there, right? But which of the flags should be set at this point?
0 flag.
The 0 flag should be set. What about the carry flag? If I add 0 to 0, will I trigger a carry? No. What about the overflow flag? Does it make sense that adding 0 to 0 ends up with a non-negative value? It makes sense. Okay, so it's not overflow. What about the sign flag? Is 0 negative?
No, it's
No.
neutral.
All right, so the Z flag should be the only one set out of those flags, those 4 that we talked about. So now we take a look at E flags. E flags. And sure enough, well, PF is actually a we don't pay attention to PF. It's a flag in between the word. It's basically, is there a, I cannot remember what PF is, but it has to, it's really weird. It is a partial flag. So it takes a look at a portion, which is a nibble boundary of the byte. But the one that we do want to know about is the Z flag, and the Z flag is certainly set in this case.
So,
Right.
so it shows like a ZF if it's active, and if it's not, it's just not there.
That is correct.
Okay.
Yep. All right. So are there any questions about this part? All right. If this works out, kind of nicely like that, now we can, write all kinds of, simple programs to experiment with. Okay, can we have this flag, set and that flag cleared, and so on? Certain combinations are not possible, but we'll take a look at some really easy combinations. Okay. I'll give you this example here. Can you guys predict what flags will be set and what flags will be cleared in this case? I'm adding 0 to 1.
The 0 flag would be cleared.
What about the other flags? We have 4 flags here. We have 0, we have carry. What about carry?
No.
Should be cleared. What about the sign flag?
Yes.
Cleared. What about the overflow flag? Should also be cleared, right? In other words, in this case, after the second add instruction, of the 4 flags that we really want to know about, none should be set. Okay? And we can reassemble the program, rerun it, and get to the result. This one I'm not even going to test, okay? Because we pretty much know for sure that is the case. What about this one? Let me move the cursor out of the way. So I'm adding 0 to 80 in hexadecimal. So what do you think would be the result of this whole thing? Well, first of all, the actual result of the addition is 80, because you add 0 to 80 in hexadecimal, you get 80 in hexadecimal. Is 80 hexadecimal 0?
No.
No. So the 0 flag is
All flags clear.
cleared. Okay. What about the carry flag? Is this going to trigger a carry operation? No. What about the sign flag? Is the most significant bit set?
Yes.
Yes.
Yes. F.
Because 80 in hexadecimal is 10000000. Okay? So the sign flag is actually set in this case.
Why not F?
Hmm?
Why not F?
F is 1111. Yep. So anything from 8 all the way to F specifies the most significant bit of that hexadecimal digit be set. What about the overflow flag? Should the overflow flag be set in this case? I'm adding 0 to a negative number and end up with a negative number. Does the sign of the negative number as a result make sense?
Yes.
All right, so this is okay. This is cool. So I'm not going to actually test it. I mean, you guys can definitely watch the video again and basically, stop frame here, type the program in, and run it through GDB. Okay, so what can I do to trigger the overflow flag to set?
Make move B 80.
Yep, that will do it. That will trigger the overflow flag to be set. Okay, now let's take a look at all the flags first. Okay, let's start with the Z flag, the 0 flag. If I add 80 in hexadecimal to 80 in hexadecimal, and remember this is a byte operation, what is the result of the operation?
0.
Is 0, exactly. Okay, 80 plus 80 is 0. It's a byte. Okay, what about the carry flag in this case?
Yep.
Carry flag is a 1. What about the sign flag?
Yep.
But it's a 0.
All right.
Okay, if it's a 0, the sign flag has to be a 0, right? Okay, so the sign flag is a 0. What about the overflow flag?
1.
Yes.
The overflow flag is a 1 because I'm adding two negative values and I end up with a non-negative value. All right, very good. Can you give me another scenario where the overflow flag is going to be set? Let's start with this one. Well, it has to do with how do we overflow the last value, or the last positive value, or the last negative value. How do we get it just one step past that point? Okay, so now the question is, with one single byte or 8 bits, what is the largest signed positive value that it can represent? Remember the number wheel itself? Okay, so when you look at the number wheel, one half of it is going to represent non-negative values. So this half, I think last time this is my convention. Okay, I should say not negative. And then the other side are the negative values. Remember this number pi thing? Okay.
7.
This starts with a 0, and because 0 is taking one slot out of this whole thing, with 4 bits, where is this guy? This guy becomes 7. And the other side becomes -1 all the way to -8. So what is the general equation of the largest positive value that can be represented by n number of bits?
7.
But the general equation is, okay, so given n bits, how do we figure out the largest value that can be represented? Go ahead.
Divided by 2 minus 1.
Say again?
So n divided by 2 minus 1.
N divided by 2 minus 1. Well, you have all the right components, but it has to be arranged like this. It is 2 to the power of n minus 1, and then this whole thing minus 1. So in this case, I have 4 bits, right? 4 minus 1 is 3. 2 to the power of 3 is 8. 8 minus 1 is 7. What about the most negative value that you can represent given n bits? It's just -2 to the power of n minus 1. All right? So every time you want to add 1 to the largest positive value that can be represented, it will flip over to the negative side and trigger the overflow flag to be set. And likewise, if you go in the opposite direction, every time you try to subtract 1 from the most negative value that can be represented, it will also trigger the overflow flag to be set. It's basically crossing that boundary. Okay, I can no longer represent that value anymore. I'm running out of bits. Yep.
So if you do move B without the add B, you just have move B, 80, would your 0 flag be set? Because the most
It would not be affected because the move instruction does not trigger any
flag.
changes to the flags.
Okay.
Yep. That's intentional inside the processor.
So it has to be one of the other.
It has to be one of the
subtract.
Yeah, it has to be one of the arithmetic operations. There are more arithmetic operations that we talk about so far, like there are shift operations, multiply, and also division. But with the instruction that we have talked about up to this point, it will be add, subtract, and compare that will change those flags. Well, we are focusing on those instructions for now. Are there any questions about these flags and how we can kind of control which one is set and which one is cleared? Okay. Now, certain flag combinations are impossible. Can someone tell me which flag combination is just not going to be possible? 0 and the sign flag. Okay, exactly. So the impossible, well, I'm going to use my notepad here. Okay, impossible flag combinations. So let's take a look at some of these combinations. Now, it is different. Some of these are operation dependent. In other words, for add, certain combinations are not possible, but those combinations are actually possible in subtraction. And then likewise, in subtraction, some combinations are impossible, but they are possible in addition. Okay? But regardless of subtraction or addition, having z equals 1 and s equals 1 is impossible. Okay? Now, since we still have the definition of the sign flag and also the z flag up, it's just like a few lines up, I think you should see the contradiction of what if they are both 1s. Does everybody see the contradiction, why it is not possible? Because if the sign flag is a 1, it means w is a 1. But if w is a 1, w or blah, 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 blah has to be a 1, but the negation of that has to be a 0. So the 0 flag has to be a 0. So they cannot be a 1 at the same time. Okay? Very good. Can someone also name, let's say for addition, some flag combinations are impossible? Okay. Can someone tell me one flag combination that is not possible for addition? Z and S takes care of a lot of other combinations, because every time you have Z equals 1 and S equals 1, it doesn't matter what the other flags are, it would not be possible. Okay, but if you focus on the overflow flag and the sign flag and the carry flag, are there combinations that will be impossible? Let's take a look. Okay, so let's say the sign flag is a 1, the overflow flag is a 1. Which value of the carry flag becomes impossible given that the sign flag is a 1 and the overflow flag is also a 1?
0. 0.
Carry flag being a 0 is not possible?
No. It's overflow. Carry, no.
Well, let's take a look. Okay, if the sign flag is a 1, that means by definition of the overflow flag, if the sign flag is a 1, that means that this is a 1 already. We have just confirmed that, right? So that means this is a not B. This B is a 0. A is a 0. If A is a 0 and B is a 0, there's no way you can trigger the carry flag to be set. So you're absolutely right in that case. The carry flag being 0 is impossible. Okay. What about the flip side of this? The flip side of this is the sign flag is a 0, the overflow flag is a 1. What about the carry flag? Which value of the carry flag is now impossible?
1.
Yep, it's the other way around. The reason is quite simple. When you go back to the expression of the overflow flag for addition, if the sign flag is a 0, it means A has to be a 1, which is here, and B has to be a 1 over here. I don't even care about the values of all of the other bits. If A is a 1, B is a 1, this carry has to be a 1. Okay? So that means, this carry being a, hold on a second here. Overflow is a 1, sign is a 0. So this is A and B has to be a 1. Okay, I think we got its opposite. This has to be a 0, and this has to be a 1. So these are the impossible combinations. I flipped the polarity. Is that making any sense? What about for subtractions? For subtraction, also, some flag combinations are impossible. And we are going to do the same trick here. We will use the sign flag and the overflow flag to kind of lock down, what we are dealing with. If the sign flag is a 1 and the overflow flag is a 1, then in this equation here, we are locking down, one to one particular side. Which side should we look at with respect to the disjunction? The sign flag being a 1 means we have to focus on this side, right? Because W is our sign flag. Okay, so if we look at this side, we have not A, which means the most significant bit of the first number is cleared, and the most significant bit of the second number is set. Would the carry flag always be set or cleared? It's always going to be set, okay? Because the carry flag is the same thing as a borrow flag, okay? In hardware, they are exactly the same thing. So that means, the impossible combination is for the carry flag or the borrow flag in this case to be a 0. Is that making any sense? Sort of? Okay.
It would be like 0 minus.
Yeah, it would be 0 blah blah blah
0
minus 1 blah blah blah.
And so you would need the borrow flag.
Exactly, the borrow is triggered, just because of that. Yep. So that makes this combination impossible, okay? Because the carry flag has to be a 1, given that limitation, given that restriction. So that means the opposite is also going to work too. If the sign flag is a 0 and the overflow flag is a 1, the carry flag being a 1 is impossible. Because in this case, we are now looking at the opposite side here, being the sign flag being cleared, which is not W. So in this case, you have 1 blah 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 minus 0 blah blah blah. Well, it's not going to trigger the borrow flag. So the borrow flag has to be a 0, and this makes C equals 1 a impossible combination. Are there any questions about why some of these flag combinations are impossible?
This is assuming that the 0 flag then is set because we're like
The 0 flag
in all these cases the 0 flag would be set to 1.
That is a good question. Okay, that's a very good question. The question is, in all of these combinations, let me just highlight those 4 combinations. Okay. Okay. In these combinations, oops. Okay. In these combinations, what about the 0 flag? Can the 0 flag be set at the same time? That would be the question. In some cases, yes, but in some cases, no. Okay. In the case of addition, yes. So in the case of addition, if you look at the sign flag being cleared, the overflow flag being set, the Z flag can also be set at the same time, because you have 80 plus 80 in hexadecimal being 00 to take care of that. But when you do subtraction, it does not work. When you do subtraction, there's no way for the overflow flag to be set and yet the 0 flag to be set also. Because if you get a 0 in the subtraction, how can you get a 0 in the subtraction? There's only one way to get a 0 in the subtraction. The 2 numbers have to be the same. So that means you have a positive number minus a positive number being 0. The sign flag makes sense. You have a negative number minus a negative number being 0. The sign flag minus the exactly. Or the overflow flag is going to be clear. All right, very good. So I think we're getting a pretty good handle on these flags, at this point. Okay. So now the next question is, okay, it's great that we can come up with these impossible combinations. and explain why they are not possible. But I still have not explained, why do we have these flags? What is the significance of these flags? And, how do we use these flags, in an actual program? What do you think?
Does it transfer the flags to another bit?
The flags are the only thing that we can use for conditional branches. That's why they're useful.
Such as like when you're transferring from AL to AH, maybe in the same area, would the flags affect that AH?
What do you mean by transfer?
Does not affect flags.
If you're doing a move instruction, the flags are not affected. Okay?
It's
The
like
most-
in C you have if type.
Exactly.
If
Okay.
else.
So I'm going to change the order of these introductions just a little bit. Okay. So at this point, I'm going to introduce the conditional branch instructions and the unconditional branch instruction. We'll talk about the easy one first. The easy one is the unconditional branch instruction, which is the jump instruction. Jump is the same thing as go to. Okay, you give it a label, and it will continue execution at that label. Is that okay?
So unconditional.
Unconditional. This is unconditional. It is just a go to, a simple go to. Now, how do I test, make a program to test this? The unconditional branch instruction. How do I make a program to make sure that, oh, okay, I see this instruction is continuing execution at that label?
Set L1 and then add a byte, then re-go and reset it.
Okay, that's one way to do it. Can we write a program simpler than that?
Jump to the end.
Jump to the end. Okay, that's another one. Okay, but it's still longer than what I want. Okay, let me show you this program. Okay, so we'll call this our first loop program. Dot text, which is probably not necessary, but I'm going to put it here. Underscore under dot global underscore start as a label. What about this? Wouldn't that do it?
Like
Because where is the jump instruction? It's the very first instruction of this entire program.
So
Do
if-
I have a label for that location?
Yes.
And that label turns out to be
Alright.
underscore start.
so this is the infinite loop.
This is the tightest infinite loop you can write. Okay. Are there any questions about this program being, an infinite loop and it's not going to exit? Well, you know what? I'm still going to assemble, link, and run this program for one purpose. There's a reason why I want to show you this. I mean, you guys are going like, yeah, but we're just going to be looking at the cursor blinking. What is the whole value of, watching that? It'll become clear.
Flags.
Effectively, I'm turning this, PC into a heater. Of course, I have to start up multiple processes to use up all of the, cores and all the.
So we're not supposed to
threading.
do on the server. Just
I've seen people doing it on the power server. It's like, no, don't do that. Okay, so I'm going to run the program, and not surprisingly, the program is doing what it is exactly supposed to be doing, right? It's an infinite loop. It does not get out, and it just says, okay, I'm still running, Okay, so what is the whole point of doing this? What if your program is doing this for homework assignments like 2 weeks later? What are you going to do? Well, your program is not going to be a tight loop like this. In other words, your infinite loop probably has many instructions involved in between, right? So you might want to know where you are in the infinite loop, or what is at least one of the instructions in your infinite loop. Does that make any sense? Okay. So how do you know? Well, the easiest way to do it is Control-C. See, Control-C would interrupt the program. In other words, it pauses the execution of the program. But by doing that, it also shows you the instruction where it is stopping at. So now, well, assuming your program is not just, label, go to the same label, then you might get some useful information, because it will show you this instruction is a part of an infinite loop. Now, it won't be able to show you all of the instructions that are a part of the infinite loop, but at least you know, okay, this is a part of the infinite loop. Yep.
If you have something that's continually, like you said, was an infinite loop that just went back to start, but if you had a loop that, say, took up multiple layers of code,
Yeah.
and it kept printing out more things over and over again, when you hit Control-C, does it put you at exactly where you hit Control-C? So like, let's say you would
Yes.
print EAX, print EAX, and then you change EAX, print EAX, and then you do a jump, and then like when you hit Control-C, say it's right in the middle of one of the prints, is that going to tell you where it ended?
It will tell you exactly where the program counter is when you press Control-C.
Okay. So
Yeah.
you might not be able to figure out what's causing the infinite loop, but you could know where.
But you can use
You
step.
can at least
You can use step.
You can then single step, right?
Okay.
If it is a loop and it's infinite, if you single step, then eventually you will get back to the same point where Control-C is breaking out, and that will give you an idea of where is what instructions are involved in your infinite loop.
You can use
That makes
step,
sense.
step by
Single
step.
until
Yeah, single step. Just single step it. Until you say, oh, okay, I'm getting back to the first point now. That becomes one iteration of your infinite loop.
Right.
Now, your infinite loop may not have exactly the same pattern depending on the logic of your infinite loop. In other words, in one iteration, it might involve lines 1, 2, 4, 8, and in the next iteration, it might involve lines 1, 2, 7, 8, 10, and then back to line 1. Okay, but at least it gives you a clue of where your infinite loop is located in your program. So it will still be useful. Yep.
Could you make an even tighter infinite loop with L1 and jump L1?
It's the same one as jump to _ start.
Yeah, but this is 2 lines.
Sorry?
This is 2 lines.
Oh, if you don't like the 2-line thing, that's easy. How's that? That will solve that problem, right? All right. Well, that's an unconditional branch instruction. Now we want to talk about the conditional branch instructions. I mean, surely this program is very exciting to watch, and it's very useful. But I would say conditional branches might actually be more useful for your programs, right? Okay. So let's take a look at the conditional branch instructions. The conditional branch instructions. If you go back to the notes, I want to show you where you can find information about that. We are now on to topic 3, and in topic 3, these are the instructions. In topic 4, we'll start to talk about the jump instructions. I'm skipping a little bit ahead of time because I want to show you what the flags are for before we go too deeply into, here's the L flag, which is a combination of the overflow flag and the sign flag. But I want to show you what they're really useful for before we go back and continue with the discussion of the flags. Okay. So let's think about this. Okay. So if I want to implement something like this in C++, how am I going to do this in assembly language? Okay. So I would say if EAX has the same value as EBX, I want to do something. Okay. Let's say I want to add 1 to EAX in this case. Else I want to add EBX, add 1 to EBX. Okay, this is what I want to do in an assembly language program. I know it it requires semicolons and stuff like that, but this is pseudo C++ code. It suffices to indicate what I want to do. Okay, so the question is, how am I going to do something like that? Well, we know how to do the comparison, right? CMP is going to do the comparison. Okay. All right, so we'll start with the components that we already know. CMP, and let's make it CMPL to make sure that it is a 32-bit comparison. And we'll put EAX on one side and EBX on the other side. Technically speaking, you do want to know which one is being subtracted from which one, because in this case, I'm subtracting EAX from EBX. But because I only care about equality, it doesn't really matter. Okay, I can flip the operands and still get the same result as far as equality is concerned. Is that making any sense? Okay. So let's say EAX, and well, let's do the other instructions first. Okay. So at some point I want to increment EAX. So that's pretty easy to do. This will increment EAX using only add L, which is adding the first operand to the second operand. I use an immediate operand to indicate, yes, 1 is the value that I'm trying to add, and then the destination is EAX. Is everybody convinced that this is the same thing as incrementing the value of EAX by 1? There's also an increment instruction, but I just want to recycle instructions that we have already talked about, and this is one way to do it. And there's another instruction somewhere that I want to use to increment EDX. So now the question is, what do I use in between all of these things to implement a simple conditional statement in C++ or C or Java, doesn't matter. Okay, after the compare instruction, which flag do I really care about in this case?
0.
The 0 flag, okay? Do I care about the sign flag, the overflow flag, or the carry flag in this case? No, because I just need to know whether they are the same or not. Whether the numbers are signed or not, take any, should I take it into consideration when I'm comparing for equality? Nope, okay? Because equality is the same regardless. Okay, great. So what I want to do here is, if I can just write something in C, semi-C, this is what I want to do. I want to say, if the Z flag is not 0, no, if the Z flag is 0, I want to go to a label L1. I'm going to stash in the label L1 over here, and if not, I'm going to perform this operation. And then I want to use, this is C code again, go to label L2, and I'll put label L2 over here. Okay, I know I'm mixing up, assembly language and, C language here, but is this logic kind of capturing what I wanted to do? I perform the comparison first, and then I take a look at the result of the comparison, and I'm focusing on just one flag in this case, just the 0 flag. If the 0 flag is clear, which means these two numbers are not the same, I'm going to say, let's go to label L1. What is label L1 going to do? Increment EBX, and I'm done. Okay? If ZF is actually non-zero, which means the result of the comparison is equal, what am I going to do? It's going to fall through the conditional statement, and it will execute add L $1 to EAX, incrementing EAX. Why do I need that extra go to L2 after that? What if I take that away? Go ahead. It's going to fall through, right? Because if I don't have a go to before L1, there's no one to tell me to continue execution somewhere else. So after add L1, add L $1 to EAX, I will actually continue to the next instruction, which is add L $1 EBX. And that's why I need that extra go to L2 in order to, we are done with the then case of this conditional statement. Let's go to the end of the entire conditional statement. That's what the unconditional go to is for. Yep.
That's not the actual assembly language.
No, it's not. So I'm going to convert it now. This one is the easy one to convert. How do we convert this to
jump?
Exactly. And this one is actually not too hard either. It is JZL1. Okay, so I'm going to comment it out so that we can say, if I want to do this, have the same effect as that C statement, I'm going to use JZL1 as a assembly language instruction.
That's it. That's all you need. JZL1.
Yep. JZL1 means jump to L1 if and only if the Z flag is set. That's basically what it says.
And then Z stands for the Z flag.
Exactly.
That's what the Z is. Okay.
Yep.
Gotcha.
Yep. It basically says jump if and only if Z.
And so if Z is 1.
Right.
And then if you did like JC,
then it's jump if carry is set. Or if you say J and Z, that means when the Z flag is clear.
J and Z?
Yep. You can negate a flag also. Yep.
Okay.
There's one more thing, like this statement is on one program?
Yeah, that's one single program. I mean, it's.
Statement, right?
I'm trying to implement this. Okay, this makes it kind of more C-like, for those of you who are more specific. So if I want to implement this logic in C++, I will need these instructions in assembly to accomplish the same thing. Yep, go ahead.
BG
J and Z because you're testing to see if the zero.
Oh, you're right.
flag is not set.
Okay, you are absolutely right. It should be J and Z because we are jumping when the Z flag is cleared, not when it is set. Thank you. No, the if statement is only stating what J and Z is trying to do. Because I'm trying to relate assembly language instructions to something that you already understand. Say again? Those are the lines that I want to implement in C. In other words, this specifies what I want to do, and this specifies how I'm going to do it in assembly. Yep.
How are we comparing two registers by comparing the flag is set or not?
That's how this is exactly how we're going to do it. We use the instruction compare long, and then with the two registers, that will do a subtraction basically, but without storing the result into the second operand. And because it's a subtraction, in the subtraction, how do you set the zero flag? They have to be the same, right? All right. So I think I'm hoping that this is helping you to understand why we have to talk about the flags and why they become useful, okay? This is the most basic and the only mechanism for a program that you write to sometimes do something like this and other times do something else. Conditional branches.
All conditional branches is based off of the flag.
Yep. If it is based on comparison. Okay. So what we'll do on Thursday is we'll continue with this topic. But the question now is, how do we find out which number is larger? Okay? In other words, we're not checking for equality anymore. I want to know which number is the larger one. Now that one is tricky because now whether a number is signed or not becomes important. The test will include everything up to the addressing mode. I think I'll probably leave this out of the first hour. Yeah. Which means, yeah, go ahead. What format is the test going to be in? I'm going to use some of the past exams as a practice exam, so you kind of know how it is done in the past. You can actually go back in at least 2 years and listen to and watch the YouTube of the past 2 years. And because after each exam, I explain the answers, so you can actually tell exactly what question I asked each semester and the answers to those. But I would go over that next Tuesday.
Okay.
Yeah, next Tuesday is our practice exam day, and then 1 week after that is our actual exam.
Should we look at the practice exam that's actually on our Moodle? Or
Yeah, it wouldn't hurt.